Welcome back to the hands-on machine learning with PyTorch playlist. In the last videos, we explored the fundamentals of linear regression. We began with a univariate linear regression where we predicted continuous values using just a single feature. Then we moved on to multivariate linear regression where we included multiple features to build a more powerful prediction model. If you haven't watched those videos yet, I recommend checking them out to build a solid foundation first. So in today's tutorial, we're stepping up our game. We will be working with a real-world dataset, the Pima Indians Diabetes dataset, to build a binary classification model using PyTorch. This means that instead of predicting continuous values like prices, now we will be predicting a yes or no outcome, specifically whether a person is likely to have diabetes or not based on various medical features. This is a crucial step in your ML journey, as most real-world problems from spam filtration to medical diagnosis are classification problems. So let's dive in and see how we can prepare real-world data, build a neural network in PyTorch, train it, and make accurate predictions using it. So like I said, we are working with a popular real-world dataset called the Pima Indians Diabetes dataset. This dataset was collected from female patients of Pima Indian heritage who are at least 21 years old. The goal is to predict whether or not the patient has diabetes based on the number of diagnostic medical measurements. So let's take a look at the features in this dataset. The first one is pregnancies, which denotes the number of times the person has been pregnant. The second feature is the glucose, which says the plasma glucose concentration, which is a key indicator for diabetes. The third one is the blood pressure. The fourth one is the skin thickness, which gives a number of triceps skin fold thickness in millimeters. Another one is the insulin, 2-hour serum insulin. And then the other one is BMI, which is the body mass index. Diabetes pedigree function, which scores the likelihood of diabetes based on family history and then a person's age. And then we finally have an outcome, which is going to be our target value or target label. A value of 1 indicates that the patient has diagnosis, and a value of 0 means that they do not. So this dataset is often used in medical and health related ML projects and is ideal for beginners to learn binary classification. So by the end of this tutorial, we'll use these features to train a neural network that can predict whether or not the person is diabetic based on their medical data set. So first, we'll start by importing our required libraries and then exploring the data set here. So to begin with, we import the pandas library, which is essential for data manipulation in Python. We then load our dataset using the readCSV function of pandas and store it in a data frame called df. So this dataset contains medical information used to predict diagnosis. Using df.head, we display the first few rows to get a sense of what the data kind of looks like, the column, the feature names, and sample values. We then check for any missing data using df.isNull.sum because missing values can interfere with the model training. Then finally, we call the df.describe function to generate summary statistics for each feature like mean, minimum, maximum, and quartile values. So this helps us understand the distribution and scale of our data, and it's a crucial first step before data cleaning or preprocessing, which is also known as exploratory data analysis. Now that we've explored the dataset, let's prepare it for training. First, we separate the features and the target. We drop the outcome column from the data frame to create X, which contains only the input features, and we store the target labels, which is the diabetes outcome, in Y. Then we use train test split from scikit-learn library to split the dataset into training and testing sets. We set aside 20% of data for validation and use a random seed of 42 to make sure the results are reproducible here. So after that, we perform feature scaling using standard scaler. Now this is again an important step because I've talked about it in my earlier videos too. This is important because neural networks train more efficiently when the input features are on similar scale. Then we feed the scalar to the training data and then apply the same transformation to both the training and validation features. This ensures that all the features are centered around 0 with a variance of 1, which helps the model converge faster during training. Now that we prepared our data, now let's convert it into a format that PyTorch actually understands. So we start by converting both the training and validation features and labels into PyTorch tensors using torch.tensor. So we specify the data type here too as float32, which is the standard data type for most of the PyTorch operations. For the labels, we also reshape them using .view function so that the shape matches what the model expects, one output per example. Then next, we define our neural network model by creating a class called diabetes model that inherits the torch.nn.module function, torch.nn.module class, which is the base class for all neural networks in PyTorch. So inside the model's constructor, the init method, we define 3 layers. The first layer is the input layer. So our dataset basically has 8 features. So the input layer takes in 8 values and then passes them to 16 neurons. These 16 neurons are like detectors which begins to identify basic patterns and relationships in the data. Then we have a second layer, which is a hidden layer that takes 16 outputs from the previous layer and then reduces them to 8. Now this helps the network narrow down and refine the learned patterns, kind of like zooming in on what matters the most. And then we have a final layer. So the layer takes 8 inputs from the hidden layer and then compresses them to a single number, because we're trying to predict a binary outcome, diabetic or not. So after this final layer, we apply the sigmoid activation function using nn.sigmoid. Now the sigmoid, the function here, plays a key role in converting the model's raw output into a probability between 0 and 1. Now this is crucial for binary classification because it allows us to interpret the output as close to 0, which assumes the person is likely diabetic, or close to, because it allows us to interpret the output as close to 1, which means the person is likely diabetic, or close to 0, which means the person is likely not diabetic. So without sigmoid, the model output might output any real number and we would be able to use it for binary decisions. With sigmoid, we can simply say that if the output is greater than 0.5, then we classify it as diabetic, otherwise we classify it as non-diabetic. Now finally, we create an instance of our model by calling the model equal to diabetes model class. Now this initializes the neural network structure we just defined and prepares it for training. Now that our model is defined, let's move on to training it. So before we do that, we just need to understand 2 important things here: a loss function and an optimizer. So if you look at the loss function, we're using binary cross-entropy loss, which is kind of a go-to loss function for binary classification problems. This function measures the difference between the model's predicted probability and the actual label. So the more the predicted probability diverges from the correct model, either 0 or 1, the higher the loss. So binary cross-entropy works especially well with sigmoid functions, which outputs values between 0 and 1. So they complement each other in binary classification tasks like ours. Next, we also set up the optimizer. Here we are using the ADAM optimizer, which stands for Adaptive Moment Estimation. It is one of the most popular and effective optimizers in deep learning. Well, ADAM combines the best of the 2 other optimization techniques, which is momentum and RMS prop, to automatically adjust the learning rates for each parameter in the network. So this makes training more efficient, especially for models with a lot of parameter. We're also passing in a learning rate of 0.01, which controls how big a step the model takes during each update. Small learning rate means a slower but more stable training here. So the learning rate is kind of a hyperparameter for us. We experiment with different values of learning rate to get the most accurate result with our model. So now in the training loop, we run for 10,000 epochs. Well, it does not have to be 10,000. Again, this is a hyperparameter. We can experiment with something else too. So in each epoch, the model makes prediction on the training data. We calculate the loss and then use the backpropagation to compute gradients. The optimizer then comes into play and then updates the model weights based on those gradients. We're also storing the loss values over time to print them after every 50 epochs to monitor training progress. So this process gradually improves the model's prediction, reducing the loss and then making the model better at detecting diabetes based on the input features. After training, it's a good idea to visualize how the model's loss changed over time. So we use matplotlib.pyplot to plot the losses list, which contains the loss value for every epoch. So a downward trend in this plot, which you're seeing, means that the model is learning, the predictions are getting closer to the actual outcomes. So if the line levels up or start increasing again, it could indicate overfitting or that the model has stopped improving. So this simple visualization gives us valuable insight into the model's training behavior. Once the training is complete and then the visualization is also complete, we move on to evaluating how well our model performs on unseen data, which is the validation set. So first we set the model to evaluation mode using model.eval. Now this tells PyTorch to turn off certain features like dropout and batch normalization that are only used during training here. Then inside our torch.noGrad block, which disables the gradient calculation to speed up computation and save memory, we make predictions on the validation set using our trained model. So the model outputs probability between 0 and 1. So we apply .round to convert them into class labels 0 or 1 for binary classification. Finally, we calculate the accuracy score using scikit-learn's accuracy score function. So this compares the predicted class labels to the actual labels and then returns the percentage of correct prediction. So this gives us a quick and interpretable measure of the model's performance. An accuracy close to 1.0 means our model is correctly identifying diabetic and non-diabetic cases most of the time. Now let's put our model into action and make a prediction on a new previously unseen data point. So we start by creating a new input using torch.tensor. This new data sample has the same 8 features as the training set, like the number of pregnancies, glucose level, blood pressure, and so on. Just like we did in pre-processing, we need to apply the same scaling to the new input. So we use scalar object that was fitted earlier to transform the new data. Then we put the model in evaluation mode again and disable gradient computation to speed things up and reduce memory uses. Now this gives us a probability, a value between 0 and 1. To convert this into a class label, we round it off using .round function. So if the output is greater than 0.5, the result is class 1, which means diabetic. Otherwise, it's class 0, which means non-diabetic. And that's it. So with just a few lines of code, we're able to use our trained PyTorch model to make predictions on real world data. And that brings us to the end of this tutorial on binary classification using PyTorch. So to quickly recap, we start by discussing how this video builds on our earlier lessons on linear regression, both univariate and multivariate. So if you haven't watched those videos yet, be sure to check them out from the playlist Hands-on ML with PyTorch. So in this video, we worked with a real-world dataset, the Pima Indian Diabetes dataset, and learned how to load and explore data using pandas, pre-process it through normalization and splitting, convert data into PyTorch tensors, define a fully connected neural network for classification, train the model here using binary cross-entropy loss and Adam optimizer, and then evaluate the model on unseen data using accuracy, and finally perform inference on new data. So this end-to-end pipeline is the foundation of many machine learning workflows. Well, it's powerful, reusable, and helps build a strong mental model of how machine learning works in practice. So in the next video, we'll go one step further and explore more complex classification problems. So thank you for watching. If you found this video helpful, make sure to like the video, share it with fellow learners, and subscribe to the channel so you don't miss the upcoming tutorials in the playlist Hands-on ML with PyTorch series. So see you in the next one.